When you think about things which science has yet to fully understand, we tend to consider rather existential questions. This will include things such as dark matter, something that we cannot see nor manipulate, yet it makes up 99% of the universe. Or another is the missing link, which sets us apart from a banana-loving ape to a banana-loving ape which can build and, mostly, drive cars. Then there are a few more dubious questions we have, like, how do I cure my hiccups? Okay, but seriously, how do we not have a conclusive way to stop hiccups? Paper foxing falls into this latter group. From a museum collector's perspective, foxing is a massive inconvenience which turns manuscripts and works of art into a spotted mess that reminds us a little too much of our middle school days. It makes viewing the objects in question more difficult to even impossible at the extreme. And yet, it, just like hiccups, does not have any physical implications for the long run of the paper itself. There is a sizable amount of literature concerned with the source of foxing. In general, they fall into one of two models. The first is the fungal model. As the name suggests, this model posits the idea that the source of foxing spots on paper is fungus, and how it interacts with the paper itself. The most common species of fungus associated with foxing is that. Look, I'm a historian and a chemist. Biology is all Latin to me. Anyway, the earliest documented studies of foxing relied on naked eye observations and low-power magnification techniques. Studies from the 1950s to the 90s all mention the use of these methods, which are, to be kind, limited. However, by the time we get to the late 90s and the early noughties, more methods common to biolabs, such as culture testing, generational growth observations, and low-invasive tests were conducted. This allowed for a far better picture of what could be going on. You see, paper is a rather complex molecule. However, for the purposes of understanding foxing, we only have to look at the slightly less intimidating cellulose molecule. Cellulose forms long chains, linked together by what's called an ether group. That's two hydrocarbons, like cellulose, connected by one oxygen atom. Cellulose is a rather stable molecule in isolation, but when it is found in these long chains, the likelihood of them breaking rapidly rises. Hence, paper's propensity to rip and tear if you're not careful. Enter the fungus. After the fungus has been around for a while on the paper, sits around, has a nice meal, and then, nature calls. Of the many, byproducts which the fungus leaves behind, the one we are most interested in is oxalic acid. For those who are familiar with organic chemistry and are not dramatically scarred from their experience, the first deprotonation of oxalic acid has a pKa of 1.27, making it one of the strongest carboxylic acids. For everyone else, take my word that this acid is able to react pretty well with the other compounds, including our paper. The electron pair found on a ketone, that's the oxygen atom with two lines coming off of it, picks up an extra proton, or hydrogen atom, from the acidic environment found in the area where the fungus has grown. It then begins to break up the cellulose structure. This makes the environment unstable, and greatly raises the pH. The cellulose wants to regain a proton by any means necessary. In this model, this is achieved by one of two ways: water or dust. Dust is full of a number of elements which do not play well with paper, including iron, copper, sulfur, and potassium. Iron and copper in particular are nasty for the paper, as they tend to rust. It is this, the model suggests, which leads to the red speckles found in paper foxing. Alternatively, in the case of water, more moisture begets more fungus growth. More fungus growth means more oxalic acid propagation, a more acidic and unstable environment, and the cycle goes on and on. The fungus model remains the most popular understanding of paper foxing. This is despite any instance of successful culture growth outside of a paper environment, nor any explanation for instances of paper foxing in which the fungus simply isn't there. These unanswered questions were too much for some conservationists and collections managers to accept the fungal model, and further research was conducted. Enter the rust model. Established by no later than 2012, the rust model chose to go further than the bounds of the fungal model allowed for. One of the largest changes and its strongest merits is a fully embraced inclusion of many mainstream science techniques which became more and more common as the decades continued and conservation became more rooted in laboratory science. The best example of this is the inclusion of gas chromatography, or GC. This is an elaborate piece of equipment with a rather simple principle. A sample is fed into the machine in a liquid phase. It is then heated to a very high temperature, hot enough to make the sample enter into the gas phase. It then makes its way around what is called a column, which is a long swirl of tubing which is lined with a substance called a static phase. This column acts as a means to better separate out the many compounds found inside a given sample by literally slowing the gas down like a thick vat of syrup. At the very end of the column is a flame which burns the sample as it leaves the column, which then generates a signal that can be digitized and read. In a number of studies, it was confirmed that metal oxidation, or rusting, played a role in paper foxing, as every sample taken from the fox spots had far larger concentrations of easily oxidized metals, such as iron and copper. But you might ask, how is this any different than the fungal model? The proposed source of the metals is what sets this model apart. The vast majority of studies conducted on fox paper were interested in paper objects from the 16th to the late 19th century. With this in mind, the first and most commonly cited source of metal deposits in paper is iron gall ink, extensively used throughout this time period and even to this day in some applications. However, other studies suggest that the metal are perhaps much more inherent to the paper itself, coming from its basic ingredients and its production. Metals which enter groundwater, both from natural and man-made processes, can enter into trees and, therefore, leave deposits of various metals which can rust years later. Additionally, that same metally water has historically been used in the paper-making process, adding even more possibilities for metals to be present in the paper itself. This, among other things, supports why some paper will never fox, while others fox rather extremely, or even why some books will have whole sections which fox terribly, while other sections show little to no change at all. Still, this model is yet to address with confidence why fungal colonies are found in many examples of foxing spots, and what, if any, role they play. What's more, just as in the case with the fungal model, the rust model does not have an answer for samples of fox paper which had very small metal composition, but still exhibit these unsightly spots. This push and pull between models can lead to a sort of chicken or egg situation. Did the fungus introduce conditions for metals to more easily penetrate the cellulose structure and allow for rusting? Or did the paper always have the metal, and its rusting happens to coincide with fungal growth? This leads to a third, yet not very distinct model. This model asks boldly, why can't both models be correct in their own conditions? For some, it's just that simple. Everyone was right. What is known with certainty are the bad things for paper, which definitely contribute to its degradation. Mold growth, metal presence, be it acquired or inherent, dust, for more reasons than just rusting, and humidity. And while that may not feel satisfying, there is still more research to be done and questions to be answered.